Hello friend, welcome to ashadec.com. Today we are talking about the Pascal's principle in fluids. It states that the intensity of pressure at any point in a liquid at rest is exerted equally in all directions. The Pascal's principle is applied in a hydraulic press or hydraulic jack, where we use a small force to lift a bigger load. Let us consider a fluid element ABCDEF in the form of a triangular prism with an angle alpha as shown below. If the dimensions of a three mutually perpendicular space coordinates are considered such that Px is equal to the pressure intensity of the fluid element in the x direction, Py pressure intensity of the fluid element in the y direction, Pz the pressure intensity of the fluid element in the z direction, or the axis perpendicular to the diagonal, then capital Px equal to total pressure force on face AB EF, that is in the x-axis, Py being the total pressure force on face DCEF in the y direction, and the total pressure force on face ABCD in the z direction. Considering our diagram here, it means you have the pressure intensities on in the x-axis AB EF, that is Px. On ABCD it is Pz acting perpendicular. This is acting at an angle of 90 to this face. Then also Py is acting on face EFCD or CDEF. Now, if that information is now understood, let us consider the equilibrium of the fluid or liquid element at rest. For equilibrium, the sum of vertical and horizontal pressure force components must equal to 0, meaning that resolve pressure forces, pressures vertically, it means the pressure force due to Py in the y direction is capital Py is equal to the pressure force component due to Pz acting vertically downwards, and is going to be Pz cos alpha, because it is seen up here. Okay, because if the pressures are acting in the y direction, still the force will act in the y direction. The same thing if the pressure intensity is having a component of cos alpha, still the force due to this pressure will have a component of cos alpha. Therefore, from pressure equal to force over area, it means capital Py will equal to small y, which is the pressure intensity, times the area on which it is acting. So for example, for Py, this is area, is acting on FECD, is area FCED. Likewise, Pz, capital Pz, is equal to small pz times the area onto which it is acting, which is area A, B, C, D. Now, substituting these values up here, it means therefore P, Y, that is from 1. This is 2. So from 1 and 2, it means PY times PY times FC times CD, because the magnitude, the length of EFCD is FC times CD, that is the area of the face EFCD. So for example, if we are to bring it in here, so the pressure intensity times the area, which is FC is FC times CD. FC times CD is equal to pressure due to Z, which is PZ, times its area, which is going to be, area is AB times BC. So for us to be uniform, let us use CD, because CD is equivalent to AB according to the geometry of the figure. So CD times BC times BC. So if we, and this is CD times BC, now times cos alpha, but cos alpha is equal to adjacent over hypotenuse will give us its adjacent is ED or FC. We can also use FC here for us to be consistent. Let us use FC over the hypotenuse, which is BC. According to this, the hypotenuse is BC. So divide by BC. So bringing it in here, it means our equation becomes small py times FC times CD will equal to PZ times CD times BC times the cos alpha, which is FC over BC. So this and that one will go, this and that one will go, this one and that one will go, so that you remain with PY, the pressure intensity in the Y direction, equaling to the pressure intensity in the Z direction. Let us call this one equation A. So having considered the equilibrium of the fluid element in the Y or vertical direction, let us also consider horizontal horizontal forces on the element. So if it is horizontal forces on the element, then forces on the left will equal to forces on the right, meaning that the force due to pressure intensity X must equal to the pressure force component in the X direction due to Z, which is PZ sine alpha. If this is equation 4, then it means substituting in our values for Px, we know Px, that is the force due to pressure X, will equal to the pressure intensity in the X direction times the area. Area, according to our diagram, we have area AB, EF. So let us use AE times EF, or AB times AE. Let us use this AB EF. Likewise, PZ will equal to pressure intensity in the Z direction sine alpha times the area, which is A, B, C, D. So if I call this one equation 5, it means from 4 and 5, putting 5 in 4 will give Px more Px, which is the pressure intensity, times area times AB times AE will give us the pressure intensity PZ times the area, which is AB, times say the AB now times the width. This is the width times length now, times. So equations 4 and 5, Px AE will equal to Pz times AB times the length, which is BC, times sine alpha. But sine alpha equal to opposite over hypotenuse gives us the opposite of the angle is AE divided by the hypotenuse, which is BC. As you can see, sine alpha is opposite AE over AD or BC, because AD and BC are equal. Substituting that value of sine alpha, therefore Px will equal to AB times AE, which will equal to PZ times AB times BC times AE over BC. This one and that one will go. Then AE and AE will also go. Then BC and that BC will also go, leaving you with Px, which is the pressure intensity in the x direction, equal to Pz, which is the pressure in the z direction. If this is equation B, from the two equations A and B, we have seen that Py is equal to Pz. Since Pz is equal to x, therefore equal to Px, it means therefore that the pressure intensities in the x, y and z directions are equal. So Px is equal to Py is equal to Pz. Hence, this relation proves Pascal's principle right.